Hey everybody, we're here at the Black House, ready for another lesson. It's going to be a good one. Behind me, before we get started, there's the hearth, and of course a Himalayan salt lamp, a 70s lava lamp, lots of lamps around here. Asteroid Psyche's back there, and it's watching a half full cup of green tea. It looks red to me. They just don't make green tea green anymore. It looks all red. Let's jump right into today's lesson. It's going to be a great one. It's going to be about the master Hipparchus, and here we are. Hipparchus was, of course, before the time of Christ, and he was a great astronomer. If you remember anything, remember that Hipparchus thought the Earth was round. He knew that just about everything in the universe was round. The Earth was rotating. That's what caused day and night. He also tried to come up with the brightness of stars, a scale of that. We know that scale is called the apparent magnitude scale. He and his students went out on a beautiful dark Greek nights and cataloged the brightness of the stars. Uh, their scale was between a +1 and a +6, with 1 being the brightest. That was, of course, Sirius, the dog star in Canis Major. Now, guess what? Hipparchus didn't take into account the sun, the full moon, so his scale has now been modified as we go along. Nowadays, apparent, and this is viewed from Earth, so it's apparently this bright. Our sun comes up at a -27. Yeah, lower the number, the brighter the object in the sky. Full moon's a -12. Venus, the brightest thing in the sky, not counting the sun and moon, can be as close to a -4 like it is out tonight. Go out and see that. Sirius comes in at a -1, and this has all been measured with light meters. You photographers know about light meters. Polaris is a 2. The naked eye limit is between a +5 and a +6. Okay. Hubble can see out there towards a +28. So remember, it's very important. The brighter the object in the sky, the lower the apparent magnitude is viewed from Earth. This is an exponential scale, so every step, either up or down, brighter or dimmer, is going to be 2.51 times brighter or dimmer. So a +1 is 2.5 times brighter than a +2. Polaris is a +2 for a basic, something you can see any night of the year. Well, that leads us to the absolute magnitude scale. As it sounds, absolute is a fair contest. All stars are measured from 10 parsecs. 10 parsecs is 32.6 light years. We'll talk about those distances here in just a little bit. So if we take all the stars and line them up, 32.6 light years, remember our sun is only 8 light minutes away. It's really close. That's why it's so bright. Then we're going to have a fair contest, and we can absolutely measure the brightness of the stars doing some basic mathematics. Now, to actually do that mathematics, we had to figure out a few things, and that was we had to realize that the stars do shift. Yes, they do. In this slide, if you take a picture of a distant star, let's just say Vega, you take that picture in the winter, in December, and then take the same picture of Vega 6 months later in June, it will have shifted just a slight. It's measured in arc seconds, which is about the width of a hair. That was first measured by Friedrich Bessel. If you're from Texas like me, you always want to call him Fried Rich, but it's Friedrich. He was a German, and he measured the shift of a star in the constellation Cygnus. Everybody's drawn to Cygnus. I guess it's because it's got Deneb and it's the swan, etc. And by measuring that shift, you can do some trigonometry, some tangent equals opposite over adjacent, and you can, that parallax angle, that shift in angle, can allow us to figure out the distance to the stars, okay? So that P is a parallax angle. It's the shifting of a star. All the stars near the Earth, their parallaxes have been measured by astronomers that came before us. There's a simple formula to figure out D. D is 1 divided by the parallax angle. And that D is measured in parsecs. That's the largest unit of measure. A parsec is 3.26 light years. and it is used by all astronomers around the world. Is that a simple formula? We figure out d by taking 1 divided by that shift, that parallax shift or parsec shift. Okay. So subsequently, if you know that angle P, you can solve for D, and that's how we know. That's how we can say Betelgeuse is 642 light years away from the Earth by figuring out its parallax or parsec angle, that shift. Makes it all simple. What is the parsec? It's the unit of measure. It's approximately 1 parsec is 3.26 light years, or about 31 trillion kilometers, or 19 trillion miles. When we start talking about our galaxy and then the universe itself, we're going to be measuring kiloparsecs and then megaparsecs, so thousands or millions of parsecs. So that parsec is our largest unit of measure. Remember when we first started, we were measuring the distance to the sun and the moon, in millions of miles and kilometers. Then we defined the AU, the astronomical unit, the Earth-Sun average distance. Now we move out to light years and then, of course, parsecs. Light year, of course, is the distance light travels in a year. I always say about 10 trillion kilometers or 6 trillion miles. On this slide, you'll actually see it's closer to 9.46. And this is the motion of light throughout in a vacuum. Okay. So the light year is intricately linked to the parsec. 1 parsec is 3.26 light years. This next slide shows you the distance to different things. For example, our closest star, Alpha Centauri, is 4.4 light years. We shoot a laser, send a radio signal, something out there to our nearest neighbor. It would take 4.4 light years to get there. To get across the Milky Way, are you kidding me? 52,000 light years. That's our entire Milky Way. To the nearest galaxy, large galaxy at least, Andromeda, that's 2.5 million light years. So we're starting to get way out there as far as distances go. To determine the light year, you just take the distance in parsecs and multiply it by 3.26. So the light year is d times 3.26. Is that easy or not? Well, it's easy for sure. Well, now here we go. Everybody wake up, perk up. How are you going to solve for absolute magnitude? This is absolutely how bright a star is from 10 parsecs, okay? M is absolute magnitude. M is apparently how bright it is from Earth. And then D is the distance in parsecs. So the equation is absolute magnitude equals apparent magnitude minus 5 log D divided by 10. Now, if you're not a math genius, if you operate like me and you have a cheap $10 calculator, the way I would attack this problem is I would take D divided by 10, get the log of that answer, multiply by a negative 5, and then add the apparent magnitude. Let's go ahead and do an example. Well, before we do that, to solve for apparent magnitude, and nobody really in astronomy does this, but since it's great mathematics, if we can solve for absolute magnitude, then we can change the same equation out to solve for apparent magnitude. No one does this, but it is possible because this is a basic truth in the universe, this apparent to absolute magnitude ratio. So you can see the equation here, apparent magnitude equals absolute magnitude plus 5 log the distance divided by 10. Here's your first example. The star Deneb, you remember that one, in Cygnus, is 434.8 parsecs from the Earth. We figured that out by measuring its shift. And if we put a light meter on it, it gives us a apparent magnitude of 1.26. If you put that into the equation, take 434.8 parsecs divided by 10, get the log of that, times a minus 5 and add a 1.26 and you get a negative 6.93. So from 10 parsecs or 32.6 light years away, Deneb would be a -6. It would be well, it'd be brighter than Venus, and it would be up there close to the brightness of about a first quarter moon. It'd be incredibly bright. Example 2, we've got Fomalhaut. Remember Fomalhaut in Aquarius? It has an absolute magnitude of 1.74, and it's 7.7 parsecs from the Earth, so it's a lot closer than Deneb. Remember, Deneb is incredibly big and bright. We'll talk about that in a little bit. Your equation is there. You solve for it like you would do any equation. And you plug it in, 7.7 divided by 10, get the log, multiply by 5, add 1.74, and your answer is 1.17. It's not very bright. It's about as bright as we look up in the sky and would see Vega. And that's basically what we see when we look out at Fomalhaut. Now I'm going to post this on the Google Classroom, but here's a worksheet. I want everybody in astronomy to do this. It's going to allow you to pass the midterm. You'll be asked to figure out the parsec angle. That's just P equals 1 divided by D. D is the distance in parsecs. D is 1 divided by P. Light years is simple. Your distance in parsecs times 3.26. And then I give you some absolute and apparent magnitudes to fill in. Once you're through, there's 5 questions to analyze. I'm going to post all of this on the Google Classroom. Hope you're doing well. I'm going to post some notes. I'm going to post these slides, and I'm going to post this video. So with that, I hope everyone's doing well, and take care.